folks, here's one we did super quickly, but definitely worth taking a look at. Magnetism. Now, as we all know, there are things called bar magnets, and a bar magnet has a north and a south pole. What you need to know for sure is that by definition, magnetic field lines point away from north poles and back towards south poles. All right? Away from north poles and back towards south poles. So a magnetic field around this bar magnet might look like this. And then it might look like that, like this, and so forth. Okay? You might see a case like this where there's the end, and over here somewhere, blah, 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 there's a south pole. And, here's another south, and blah, blah, somewhere over here there's a north pole, fine. But the field there, again, points, like we said, away from north and towards south. Okay? All right, fine. That's sort of the super duper basics about magnetic fields. Now, let's see. A little intricate part that we said that's pretty neat is here's the Earth. The Earth has a magnetic field. That's why magnetic compasses work. There's the Earth. Well, the field around the Earth goes like this. Comes out of the poles, looks something like that, and the field lines go this way. That's how, that's why the compass needle points towards Santa's house when you hold a compass. Well, the weird thing is that we said that magnetic field lines go away from north and towards south. So our geographic north is a magnetic south. Our geographic south is a magnetic north. Pretty crazy, but neat. Now the other thing that you need to know about magnetism is the following. All right, you take a magnetic field like this. And then you take a wire like this, and you run current through it like that. Well, let's see. There's a rule that you don't need to know. It's called a right-hand rule. Magnetic field, so that go in this right-hand field like that. This wire ends up being is pushed or feels a force. Now, the direction of that force is weird. It happens to be what we call out of the page. So this wire would literally be pushed like towards your face in a third dimension that's outward as opposed to left, right, up, down. But the big deal is that moving charges cause magnetic fields. Oops, sure, fine. Fields up, and therefore can be pushed by them. Right? So if a moving charge makes its own magnetic field, well, a magnetic field can be pushed by a different magnetic field. Or a magnetic field can push a different magnet. Right? So moving charges in magnetic fields experience forces. All right? That's how motors work. All right? It's a bit more than we need to talk about. But how about we talk about this instead? Here's a speaker. The cone of a speaker looks something like this in there. There's that little like interior part that, and when you play your awesome bass in your awesome car, this speaker vibrates back and forth like that. Boom, 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 boom. Yeah, puts out your bass when you're listening to Lil Wayne or whoever you're listening to, right? And how does that work? Well, it works because on the back of this speaker, there's this other thing that's a magnet. There's literally a magnet back there, and around that magnet, there's a bunch of wire that's wrapped around that wire. Sorry, around that magnet. All right, and well, there could be a different. Yeah. So anyway, you run some current I in this wire, and that moving current makes a magnetic field which can push or pull on this magnet in here, and so that magnet is pushed or pulled in and out, which makes the whole speaker go boom, 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 and make it sound. All right, so big deal again. Moving charges make magnetic fields. All right, and therefore, current carrying wires can be pushed or pulled by magnets, or current carrying wires can push or pull magnets. All right, so that's the super duper quick on magnetism. Steve.